Okay guys, hi. Welcome to physics. So we're going to begin. We're not going to do the whole thing. That would take us forever. We're going to start section 10.3. Not sure which day I'm going to be uploading this yet, but I'm going to record it and have it ready. Section 10.3 deals with a brand new concept, which is why it kind of sucks that we're doing it this way. It's going to deal with something called torque. You may have heard that word in real life. If you are into cars at all, torque has to do with the amount of power that it has to speed up and slow down. So we're going to talk about this, Wicket, stop. We're going to talk about this concept of torque. Just a sec. Stop. Sorry. So I'm going to upload the PowerPoint for this so that you have the notes on it, but I just want to be able to explain it a little bit so that hopefully the notes will make sense. So if you had a ruler, okay? If you had a ruler and somebody pushed on it at that end of the ruler, and somebody pushed on it that way at that end of the ruler, and they both pushed with equal force, no motion would happen. And it says the net force on the ruler is 0, but it could begin to move depending if this person maybe pushes. Actually, even if you push with equal force, it's going to begin to move. So if I push this way and someone else pushes this way, it's going to... Will you two stop? Good grief. It's going to move, but it's not going to move across. What's going to happen is it's going to start to spin. It's going to start to turn. That spinning... I have a dog spinning on my... Just a second. Stop. Go away. Go. Be gone. Not you guys. All right. So that turning force, so hard to do at home. This turning force is what's called torque. This turning thing is what's called torque. He is trying to get away from you, Wicket. Go away. So when working with large objects, there's actually two types of motion. There is translational motion. Translational motion is the motion that we've been working with so far. Things moving one way or another. So if I walk across a floor, that's translational motion. But then there's rotational motion, and that is that spinning motion, that things moving in a circle. It doesn't actually get you anywhere. Wicket does it constantly. He spins always to the left. It doesn't get him anywhere. That's torque. So something can actually have both translational and rotational motion at the same time. If you throw something, it has translational motion because it's moving across the room. But if it flips like end over end, like if I threw this whiteboard marker and it flipped end over end as it went through the air, it has both rotational motion and translational motion. So the rotational motion is what's called torque. Now, you probably know more about torque than you think you know about torque. When you were a kid and you would play on a teeter-totter or a seesaw, depending on where you come from, who knows what you call it, you knew that if you were the little teeny kid, like I was, and some big kid, I'll be nice and say big kid, some big kid came and sat on the other end, that the teeter-totter wasn't going to work very well. And you either had to get more kids on your end, or you could shift position. If you came closer to the pivot point, if you came closer to the middle, that would actually help the seesaw to work better. And you just figured that out as a kid, but that actually is a lot of physics involved there. And so where the pivot point is the point that it spins around or moves around on. If we were at school, I would be opening and closing the door at this point, because when you open a door, that's actually torque, all right? So let me draw a picture of a door. So if you have a door and your hinges are here and your door handle is here, the pivot point is on the hinges. The door pivots around the hinges. Oh my word. I'll go viral just because of the dogs growling in the background. Sorry. So I'm totally losing my train of thought now. So the pivot point is on the hinges. You actually apply the force here on the doorknob. You are pushing and pulling on that doorknob. Sometimes in really fancy places or in really old homes, the doorknob isn't actually placed here. The doorknob's actually placed in the middle of the door. But think about how that would actually work. Why do we put the doorknobs way over here? Why don't we put the doorknob way over here near the hinges? If you tried to open a door and the doorknob was over here, it really wouldn't work very well, right? Like, how would you get that open? There needs to be a certain amount of distance between the pivot point and the place where you're applying the force, all right? And so the force is being applied here, the force is being applied here. The pivot point is here. The distance between where the pivot point is and where the force is happening is, we call it R, and R is what we call, it's the term they use for it is lever arm distance. They call it a lever arm because it's like a lever. Like you have to have a certain amount of distance in here in order to make it work properly. So this is called the lever arm distance. The force is how much force are you applying on this doorknob to actually make it open. Now, if we had a shorter lever arm distance, we would have to apply more force. They are proportional to one another, right? They work together. And so there's a formula, of course, for torque, just like in everything in physics, there's a formula for that. There's a formula for torque. Torque is represented by this funny looking T. I believe in the Greek it's called tau, but I'm not sure. And the lever arm distance is R, and F is the force. The force and the lever arm are always going to be perpendicular to one another. That's really important. So in this case, think about a door. The lever arm distance is going across the door, but you are applying a force in or out. You are applying the force like this way, or you're pulling this way. I can't do 3D. All right, but you're either pushing the door in or pulling the door out, but the lever arm distance is going across. They are perpendicular to one another. In the textbook, they actually put a little perpendicular sign here on their R just to remind you that those two things have to be perpendicular to one another. And everything pivots around its center of mass. Center of mass, you can think of it this way. If you had a ruler and you were trying to balance the ruler on your finger, the place where the ruler would balance and not tip to one side or the other is called its center of mass. We talk about center of mass when we talk about gravity because we always in physics assume that gravity is working on your center of mass. And center of mass really has a lot to do with balance. We talk about with guys and girls a lot. With guys, their center of mass is actually higher than in a girl's center of mass. A little while ago, there was a chair challenge going around where you set a chair up against the wall and then you leaned over. We did this in class one day just to goof around. And guys have a really hard time if they have their head against the wall and they are leaning over. They have a really hard time picking up that chair. And again, that has to do with center of mass, where a guy's center of mass is higher. So he's actually working, that's why he has more upper body strength, because he's working more against gravity higher up, whereas a woman's center of mass is lower down. That was just an aside, had nothing to do with anything. So we're going to do a model problem on page 493. On page 493, there is a model problem. We're going to go through this together, and then I will let you try a couple. I have a notion. There will be questions on those. So if nobody asks me any questions, I'm going to wonder why. Because traditionally, there are questions. So the model problem says you have a cable that is attached to the shaft of a 395 kilogram crane. So the mass of the crane is 395 kilograms at a point 4.5 meters from the hinged pivot point. That is your lever arm distance. The lever arm distance, so from the place where the hinge, where it's going to rotate around, to where the cable is attached is actually 4.5 meters. I'll draw a picture of this in a minute. When the crane is horizontal, the cable makes an angle. You knew angles were going to come into this, right? Makes an angle of 55 degrees with the crane and pulls on the crane with a force of 1,250 newtons. That is a force. What torque is the cable exerting on the crane? By the way, I forgot to mention, it'll be in the PowerPoint, but I'll say it out loud as well. If torque is positive, then that actually means that it is rotating. Hold on, I want to say this right and not backwards, because you know me, I will say things backwards. If torque is positive, it means that the object is rotating counterclockwise. So in elementary school, supposedly they no longer teach clockwise and counterclockwise. Here's the reason why you need it. So counterclockwise, again, would be going that way. So if torque is positive, if you figure out your torque and it turns out to be positive, it means the thing is spinning counterclockwise. If torque is negative, then it means that the object is rotating clockwise. So in other words, it's going that way, right? All right. So for part A, what we have is this. So you have a crane, and so here's the crane, here's the arm of the crane. Okay, there's the arm of the crane. This arm can move up and down. It's hinged right here. There's a cable attached. Right? And there would be a pulley up here that the cable would be attached to. But the cable is attached to the crane so that you can pull on it to move that crane arm up and down. It will rotate. So we know that the lever arm distance is 4.5. Okay, so we know that the length to the cable, we know that this is 4.5. I shouldn't say that's the lever arm distance. Is 4.5 because it's actually not I should just say, sorry, let me apologize and relabel that. The length of the crane arm, is 4.5, and this is the cable that is attached. Okay? So the force that the cable is applying here is 1,250 newtons. Okay? Now, remember that I said the lever arm distance is always perpendicular to the force. And I said that was important and it would come back. It's coming back right now. All right, if this is the cable and the crane operator is he's got the tension on the cable is exerting a force up that cable because it's trying to hold that crane arm up. So the force is going this way. All right? I apologize a lot for them. Stop, Gabriella. If the force of the cable is going this way, the lever arm distance must be exactly perpendicular. This line is not perpendicular, so that line is actually not your lever arm distance. That's just the length of the crane arm. This right here, making a perpendicular line right here, this is actually your R. This is your lever arm distance. Again, your lever arm distance has to be perpendicular and it has to go from the pivot point, which is here, to where the force is happening. And the force is happening along this cable. So it has to be a perpendicular line from the pivot point to the cable. So what I have created is a right angle triangle here. I've got this right angle triangle right here. And we know an angle, 55 degrees. So how did they describe that 55 degrees? They said that the cable makes an angle. The cable makes an angle of 55 degrees with the crane arm. So that is the angle right here. So torque, still barking down there. Torque is lever arm distance times force. All right, well, we already have a force. We have that the force is 1,250. What we don't have is we don't have the R. But we can figure out the R because we know trig. I'm teaching it to my grade 9s now, so you can tell them you actually do use it. Maybe not in real life, but at least in physics life. So if I want to figure out what R is, that would be my opposite side, and I know my hypotenuse side, so that would be sine of 55 is R over 4.5. So my R would be 4.5 times sine of 55. So whatever that is. So 4.5 times sine of 55. That is 3.686. And it keeps on going, but whatever. So you can either just do 4.5 times sine of 55, or you can put in the value that you actually get. And so my torque works out to be 4,608. In terms of significant figures, there's only 2, because they only gave us 2 right here. So that would be 4,600 or 4.6 times 10 to the third, one of those 2. And torque, well, let's look at our units. Force is measured in newtons, lever arm distance is measured in meters, and they're multiplied. So there is no name for what we measure torque in, it's just newtons times meters. Not newtons per meter, but newtons times meters, okay? So it's 4.6 times 10 to the third Newton meters is what that is. So that is part A. Part B. Oh, and by the way, the torque was positive, which means it goes counterclockwise. And if you think about it, if the force of the cable is going up this way, that is going to pull that arm this way, and it would turn, right? If it kept going, it would end up going around counterclockwise. The next part of the question says the crane is 5 meters long. So the cable's attached here, but they're saying the crane would extend out further than that, okay? The crane is actually 5 meters long, and its center of mass is in the middle of that. So again, remember when we talked about center of mass like back 5 minutes ago? When we talked about center of mass, we talked about that kind of that balance point. Where would it balance? It says that if the crane is 5 meters long and its center of mass is in the middle of that, what torque is the crane's weight exerting on the crane? So, in other words, if this cable wasn't here, all right, if this cable wasn't here holding this crane arm up, just by virtue of the crane sitting here in midair, there would be a torque on it because gravity would be pulling down on the crane arm and pulling it down. Now, if this was a hinge and it could freely spin, it would just fall down. But even if it's not, torque is still working on it. Torque is still there. It's just that the joint here is strong enough to withstand that torque, and it doesn't fall. But now they're saying that the length of the crane is 5 meters. So we're going to forget the fact now that there's a cable there. We're going to say, what if there wasn't a cable there? And the length of this is 5 meters, and the center of mass is exactly in the middle, which means the center of mass would be at 2.5 meters because that's halfway, right? Half of 5 is 2.5. And so it wants to know what would be the torque that is working on this. So again, torque is lever arm distance times force. Now again, we're pretending there's no cable there, so there's no 1,250 newtons of force of the cable holding it up. Right now, the force that is working is just gravity pulling down on that crane. That's the only force that's there. So, when we figure out the torque is the lever arm distance. It is the distance from the center of mass to where the pivot point would be. So the pivot point would be here, the center, and we assume that gravity, I kind of drew that in the wrong spot, but it's because I had a number in the way. We actually assume that gravity is pulling on the center of mass. That's where we assume the gravity is working. So if gravity is working on right here, that's where the force is happening. The pivot point is here. That means that the R is 2.5 because the distance. And so again, notice that they are perpendicular. The R, the lever arm distance, and the force are perpendicular to one another. So this one's actually easier than the last question because we don't have to deal with any angles or anything, because this and this are already at right angles to one another. So the lever arm distance is 2.5. The force is the force of gravity. And we know that force of gravity is mass times acceleration due to gravity. They told us that the mass of this crane is 395 kilograms. And we know that acceleration due to gravity is 9.81. And so when we do this, it works out to be, and I'm cheating, I'm not putting it in my calculator, I'm cheating and looking in the textbook, guys, sorry. They say it works out to be 9,687.4. And again, paying attention to significant figures, that would be 9,700 Newton times meters. So Newton meters, or 9.7 times 10 to the third Newton meters. The only thing is we have to think about signs here. It doesn't just work out nicely unless we really think about signs. You could think of it this way. I'm going to explain it a couple of different ways. You can decide what makes sense to you. You could think about it this way. If you assign that down is negative and the force is going down, then the force would be negative. I would just make my acceleration due to gravity negative because down would be negative. And so that would make this whole thing work out to be negative. So you could do it that way so that it work out to be the right sign, or you can just think about it kind of logically. We already discussed that if it's going to spin counterclockwise, then that means torque should be positive. If it's going to spin clockwise, then my torque should be negative. And just thinking about it, if there's no cable holding it up and this thing starts to move, gravity is going to start pulling it this way. And it would actually, if it kept going in a circle, right, if it starts heading this way, it's going to go clockwise, which is negative. So I can just put the negative there if I need to. Otherwise, you need to be thinking about down would be considered a negative force and up would be considered a positive force. It's up to you. We're only going to go over that one example because that's a lot. So we're only going to go over that one example today. And you'll be doing numbers 29 and 30 in your textbook on page 495. But this probably isn't going to be posted for a few days yet. So I know that doesn't mean anything to you because you're just seeing it now for the first time. I'm just thinking out loud in my head because I am crazy Mrs. Gocher. All right, so we'll talk to you again soon. Bye.